Math 2414, Trigonometric Substitutions, Video 7, Summary for Using Tangent. In the previous two videos, we integrated expressions containing the square root of x squared plus 1 and the square root of x squared plus 4. In this video, we're going to generalize the concept and just work out a couple of examples, only deciding with a trig substitution, not actually doing an integral. When we integrated the square root of x squared plus 1, our trig substitution was x equals tangent of theta. But when we integrated the square root of x squared plus 4, our trig substitution was x equals 2 tangent theta. The 2 basically came from the fact that 4 was 2 squared. So in general, when we are integrating an expression of the form square root of x squared plus a squared, our trig substitution will be x equals a times tangent of theta. And I'll be honest with you, it doesn't even have to have the square root over it. That's just part of the examples that we've seen. Really, the driving force, addition problem, collapsing to a single term by using the substitution. Let's take a look at a few examples of determining the trig substitution. Let's say the integrand contains the square root of x squared plus 256. Now, you may or may not recognize 256 as a perfect square, but this kind of prompts a little what I call thought cloud. This is what you would think, not what you would write. Is 256 a square? Well, the easiest way to see if a number is a square is to square root it using the technology of your choice. If you were to square root 256, you would get exactly 16. Therefore, you could conclude that 256 is 16 squared. And again, you can just think this and do this in a calculator. Yeah, 256 is 16 squared. So if we did that, what would our trig substitution be? Our trig substitution would be x equals 16 tangent theta. Remember, the number in the front of the tangent is going to get squared and match this number so that we can factor it out. What about this one? Is 12 a perfect square? Well, of course not. Do you know the square root of 12? Well, it's a nasty decimal, but we can simplify it by splitting off the square root of 4 and then square rooting just the 4 and leaving the 3 behind. So when you're using a non-perfect square in your trig substitution, can you say something like the square root of 12 times tangent of theta? Of course you can. But in your final answer, if there are any square root of 12s lurking around, you would be expected to do that too. Go back, I want you there. All right. So what about that last one? Square root of 25x squared plus 16. Well, this is the same phenomenon we saw when we summarized using sign for a trig substitution, in that the coefficient of the x squared might not be the number 1. Can we develop a technique? Of course we can. But I personally think it's critical to understand what's going on so that when things change, you can adapt. What do I mean by that? Well, we're trying to take advantage of the trig identity, tangent squared theta plus 1 is equal to secant squared. And so our choice of substitution was based on trying to match our addition problem with this addition problem. And the trick that we did was to try to transform the 1 into the correct number. So we would multiply this expression by 16 in order to get the plus 16s to match. Then we would equate the variable parts. We would get 25x squared equal to 16 tangent squared theta. Then we solve for x, we would divide both sides by 25. Actually, let's do this. We would divide both sides by 25, and then we would square root both sides. And if we square rooted both sides, we would get x equals 4/5 tangent of theta. Can we generalize this? Of course we can. We could replace the 25 with b squared, the 16 with a squared, the 5 with a b, and the 4 with an a. But I'm not as worried about coming up with generalizations. Really, generalizations are just ways to tell a machine to do calculus. When something looks like this, do that to it. But I'm more concerned with the underlying principle that we're trying to take advantage of a trig identity and then using that to motivate the substitution. All right, we got one more type of trig substitution to look at, because one thing we didn't answer was what happens when we have a subtraction problem. but the variable's on the left side as opposed to the right side. When it's on the right side, our trig substitution involves sign. But what will it involve if the variable is on the left side of the subtraction?